Good morning, I'm ZhenChen from University of Science and Technology of China. I'm sorry that I have to show our work by video because of visa problem. If you have any question or interest on our work, please contact me by this email. Here is our work, Decouple and Stretch, opposed to channel pruning. We want to reduce the results requirement of deep learning in IoT scenarios. Firstly, I want to introduce some background information. Nowadays, Internet of Things has been applied in many areas, including industry, energy, health, and transport. Meanwhile, deep learning has shown superior performance on various AI and computer vision tasks. The trade is obvious that IoT and deep learning should be combined together. However, for some time-sensitive tasks, such as driving and health monitoring, sending data to centralized cloud servers would induce intolerable latency. To achieve real-time reaction, extremely tiny and efficient DLNs are needed for embedded devices and edge computing. In a word, the resource requirements of DLNs are unaffordable to resource-constrained devices. For example, VGG16 is a common model in computer vision tasks, but its parameters occupy more than 500 MB storage space. When computing a single image with specific resolution, VGG16 requires 30 billion flops and 60 MB runtime memory to keep the immediate results. Let's have a look at the current DLN's compression and acceleration works. Different from other methods, channel pruning obtains acceleration and compression benefits at the same time. Channel pruning is performed on pre-trained CNN models regarding each convolutional filter as a basic unit. The algorithm discards convolution filters that are considered to be insignificant. In each iteration, the least important filter is expected to be deleted. Then perform fine-tuning to restore the network performance. If necessary, the above steps can be repeated. Finally, channel pruning can generate a smaller network with compact structure. But channel pruning also has some shortcomings. The redundancy within filter cannot be removed. Picking the wrong filters cannot be avoided. These two problems are what we want to solve. Now come to our work. We analyze misjudge in channel pruning by a mathematical model. For CNN with M0 significant filters and M1 insignificant ones. For a certain pruning criterion, we assume that the probability that channel pruning algorithm misjudges in a iteration is invariant p. It should be noted that misjudge is not equal to damage. If the pruned filter is insignificant, the network maintains its performance. Once the misjudge happens, the probability that the pruned filter is a significant one is what we want to reduce. Principle of maximum entropy treats unknown events with equal probability. The probability of pruning a significant filter in the CNN is shown as equation 1. We shrink each filter into as smaller filters. Since the new filter contains less parameters, the misjudged damage can be reduced. In the new network, the probability decreases slightly as equation 2. The probability that equivalent damage case is reduced is equation 3. Here we found that to reduce the size of filters can reduce the damage of misjudge in channel pruning, and also avoid the severe mistake dramatically. From this perspective, we propose a decouple and stretch scheme to improve channel pruning. In the decouple step, in most cases, relatively small weights in sequence are unimportant. We eliminate the redundancy while maximum sampling. Also, the filters become smaller. The implementation is shown in the figure. In the stretch step, deeper network means larger parameter space, which is capable to solve more complex tasks. We stretch the decoupled layers with more activation functions. The whole framework is shown here. We implement DS first, then implement channel pruning. As a result, we convert the initial network into the compact, smaller network. Let's have a look at the experiments and the results. We implement experiments on CIFAR10 and CIFAR100 datasets. They are both suitable for results-constrained IoT scenarios. Our strategy focuses on the accuracy of pruned models without retraining. This is different from the previous works. Without final retraining, we implement channel pruning with or without decouple and stretch scheme. The blue curve is the performance of the baseline pruning. The red one is pruning enhanced by our DS method. Our DS scheme can improve channel pruning at different compression and acceleration rate. On CIFAR10, our scheme obtains up to 49 compression improvement and 19 acceleration improvement. The same experiment on CIFAR100, our scheme also receives 27% compression improvement and 35% acceleration improvement. When extremely pruned, the networks without recovery seem to be damaged obviously. In fact, with final recovered retrain, the pruned models obtain competitive accuracy. Our DS scheme still results in better performance with compression rate improved by 35% and recovered accuracy rising 1.6% at the same time. We also compare our method with previous work in IoT scenarios. The ADAPT method is proposed for extremely efficient and tiny sequence on the IoT scenarios, which is better than the baseline pruning method. Our DS model outperforms ADAPT with 1.25% rise in network performance and 8% improvement on model size. Finally, we evaluate the latency on hardware platform. CIFAR10 network are implemented on the specific platform without any designed hardware optimization. DS scheme induced not only 37% improvement on flops reduction, but also 42% improvement on hardware latency. So the consistency between flops and critical latency is crucial to sequence deployment on IoT devices. In summary, for better acceleration and compression on DNNs. A two-step method, decouple and stretch, is proposed to help ZhenNs perform better in future channel pruning. DS scheme improves channel pruning with up to 49 compression improvement on CFR 10 and 35% acceleration improvement on CFR 100. DS scheme enhanced channel pruning is more friendly for hardware deployment with latency reduced by 42%. Thank you. If you have any question, please contact me at this email.